Let's take another example where this is a passive optical network, which means we will talk more about passive optical network again in networking. The fact that it is passive means that there are no amplifiers in the link. Okay, this is a network that is actually allowing fiber to reach your home. The ability of all these fiber cables. The fact that your internet is of the order of 100 Mbps because of those dedicated fiber links is happening because of the fiber to the home, and typically the data rates for what are called as gigabit ponds or GPON networks. We will talk about GPON later in the networks. That is operating at 2.5 Gbps. Okay, so this is a practically realizable case. You want to design that. You can budget splice every 2 km. The splice loss is slightly different in this case, 0.6 dB per splice. What is the maximum link length and what is the allowed load resistance? Which means that we are getting slightly into a finer details of this is load resistance at the receiver. Okay. Given that the transmitter is, so you have a transmitter which is at 1310 nanometer, it is giving much larger power, minus 3 dBm. The previous transmitter was probably minus smaller power, maybe it was an LED. The spectral width was also 3 nanometer if you had noticed in the previous case, so that could have been an LED. The rise time is 100 picosecond for the transmitter. Here the spectral width is 0.2 nanometer, so maybe this is a laser. That's why it can give you a minus 3 dBm larger power also. Receiver, instead of giving sensitivity, what you are given is I need to operate at 10 power minus 10 BER, right? That's a condition given. The responsivity is 0.7 ampere per watt, which is a typical responsivity of an in-gas detector. The rise time of the detector itself is 100 picosecond, but there is an additional RC in the TIA stage, the transimpedance amplifier stage. So you have transmitter, fiber, and the receiver, which has a photodetector followed by a transimpedance amplifier, right? So this transimpedance amplifier stage has a capacitance of 1.2 picofarad and there is a resistance. So you want to find out what is the allowed load resistance. So what limits the load resistance, you need to think. I mean, it's not loss budgeting that is limiting the load resistance. It's RC time constant or the rise time of the receiver that will limit the load resistance. So what we will do is first we will do the rise time to calculate what the load resistance is about. So the system rise time, because it is 2.5 Gbps and GPON supports 2.5 Gbps in the non-return to zero scheme signaling. So the allowed rise time is 0.7 divided by 2.5 Gbps. This number comes out to be 280 picosecond. This means that put together the transmitter, the receiver and the fiber the rise time of all those three components must be less than 280 picoseconds. So this is what the formula is. Transmitter, fiber. Now in receiver there is the detector rise time, the time taken for the detector to respond, and in addition there is a TIA stage and that has an RC time constant. And so the rise time posed by the RC time constant is what we are representing as tau square RC. So let's calculate this. It means that all these numbers are known to us. What we do not know is the resistance here. So let's say that this system rise time, this right side must be always less than or equal to 280 picosecond, which means tau RC must be less than or equal to system rise time minus this, so you're just pushing everything to this side, which is 0.28 square, 0.10. Why 0? Because the fiber rise time is 0, it's again 1310 nanometer. So RC time constant turns out to be less than 0.24 nanoseconds. So RC time constant is nothing but 2.2 RLC, which we discussed earlier in the beginning of the lecture. C is given to you. So it means that my load resistance must be less than 91 ohms. So you're giving a specification to the detector that you're using, saying that the effective load impedance, the effective impedance of the load of the resistor must be less than 91 ohms. If it is greater than 91 ohm, it means that the RC time constant of the detector becomes large, and when it becomes large, it cannot support 2.5 Gbps. Okay, so you have to effectively change the output impedance of the receiver. You can play around and change it to be a number less than 91 ohm. Once it is less than 91 ohm, you can respect the rise time requirement of a 2.5 Gbps system. Okay, so here again you kind of did not face a problem because of the fiber, because you are operating at 1310 nanometer. Okay. Now this problem is not over. This is only the first part. This is the allowed load resistance. We now need to look at what the transmitted power is, or what is the longest link that is possible. So we go back to our loss budgeting. So we say that it's a pin detector. Now loss budgeting always starts at the receiver. So start with what kind of receiver you have. If the sensitivity is given to you directly, you can work back, but in this case the sensitivity is not given to you. So you start with noise, SNR, Q, and so on. So this we know it's dominated by thermal noise, and we know the thermal noise is given by 4 kT by R times bandwidth. Square root of that will give you the standard deviation of thermal noise. So here again for NRZ, we need to operate only at half the bandwidth, right? So the delta F is 1.25 gigahertz. So for NRZ, the electrical bandwidth required is only 1.25 gigahertz. Now for a BER of 10 power minus 12, the Q required is 7. So the SNR, if it is thermal noise dominated, we have proved that SNR is equal to Q square. We have derived this before. So the required Q is 7. So the Q square is 49. Now for that, it means that SNR must be greater than 49. Now SNR is nothing but receiver sensitivity. For achieving a BER of minus 12, you have this as square root of 49 into 4 kT by RL times delta F times 1 divided by RD. This 1 by RD should be outside this square root, right? So you calculate that, and that turns out to be minus 23.2 dBm. I think the question was for 10 power minus 10, the receiver sensitivity is minus 23.2. So which means you know that at the receiver, you need to have a power of minus 23.2 dBm. You know that the transmitter has a power of 3 dBm, minus 3 dBm at the transmitter. So you can now calculate what is a fiber plus, considering the splice loss, connector loss, what can be the length of the fiber. That calculation is similar to the previous. So the average power required to maintain the specific the link is not limited by dispersion, it is just limited by attenuation. Let's look at a third example where the link is now starting to depend on dispersion, because now you're going to consider 1550 nanometer. So consider a link at 1550 nanometer. It is desired to achieve 10 power minus 12 BER, 10 Gbps NRZ OK link. Transmitter line width is given. Its external modulation, average power after modulation is minus 6 dBm. Rise time, it supports a rise time for 10 Gbps, means that transmitter is not posing any limitation as far as the rise time is concerned. Optical signal to noise ratio at the transmitter is 30 dB, which means that if I take the optical spectrum at the transmitter, the signal power is minus 6 dBm and the noise power floor is minus 36 dBm, so that the signal to noise ratio is 30 dB. This is optical signal to noise ratio if I look at the optical spectrum. Receiver is spin diode, direct detection, rise time of 10 Gbps. So again the question is, here the point that the question is trying to make is that you are not limited by the transmitter or the receiver, because both of them supports 10 Gbps. It's much higher than, rise time is much lower than what is required for 10 Gbps. Responsivity is this, load resistance is 50 ohm. Fiber is standard single mode fiber, 0.2 dB per kilometer is the loss. It's a single mode fiber, so it is dispersed, it is limited only by intramodal dispersion. There is EDFA available with a variable gain from 15 to 25 dB. The noise figure is 8 dB in this range. So we are now worried about the EDFA noise figure. Question is, what is the maximum span length and find the number of, so this with this EDFA is this, with this EDFA. How many EDFAs can you use in this system? So we start by saying the loss budgeting. Desired BR is 10 power minus 12. So the required Q is 7. So the minimum SNR is 49. So that is 16.9 dB in terms of decibel scale. 10 Gbps NRZ OK. So the receiver bandwidth is only B by 2. So that is 5 gigahertz. Now that 5 gigahertz, if you convert, so this is delta nu is 5 gigahertz. You can convert that into delta lambda. This delta lambda conversion is important for calculation of dispersion. So, we know how do you do this conversion? We know that nu is equal to C over lambda. So delta nu, the frequency spacing, corresponds to C by lambda square delta lambda. So if you want to calculate delta lambda, that is lambda square divided by C delta nu. Without, of course, you know that as the frequency increases, your lambda decreases. So this is at 1550 square nanometer square divided by 3 into 10 power 8 meter per second multiplied by 5 gigahertz is going to give you this number. A rule of thumb, or rather a number that is good to remember, is that 1 nanometer corresponds to 125 gigahertz. 10 gigahertz is actually 0.08 nanometer. So these are some numbers which will come out correctly if you do it for 1550 nanometer. We know that the SNR should be greater than 49. So you substitute a signal power divided by noise power. You operate in the thermal noise dominated regime. Work out what is the received power, like how we did in the last problem. So there is so that it means that the received power must be greater than 20 dBm, minus 20 dBm. There's only one span. There's no splice loss. So loss budget in one span is minus 6 dBm at the transmitter. Of course, we are not accounting for connector loss here. If you wish, you can add a connector loss of 1 dB also. But if I don't consider any splice or any connector, it's a very tight budgeting. Minus 6 dBm, minus 20. So which means that you can allow a 14 dB loss in the link. So you have a transmitter in this case, you have fiber, you have EDFA, you have fiber, EDFA, and so on. So this is the receiver. So the first thing you are trying to calculate is, if I had kept the receiver here, what would have been the length of the span? So the question is, of course, the attenuation is 0.2 dB per kilometer. So longest length of one span is 14 loss divided by 0.2, because you have to remember that the EDFA can compensate only for the loss in the link. It loses, the power falls, so as a function of length, this is the power. The power falls as a function of length. At the EDFA, you amplify, reach the same power level. Again, because of the transmission through the fiber, the power falls, and the EDFA again amplifies, and you basically get back to the transmitted power, right? So the link length design, every 70 kilometer you can keep the EDFA, get back to the original power, right? And that can so you can calculate what the link budgeting is. Now the question is that okay for as far as the rise time is concerned? Is this budgeting, would this work if I have a rise time budget? In fact, I could in this calculation, what I could have done is, I have a transmitter. I could just compensate for this loss with this EDFA, and I could still bring it back to minus 6 dBm, right? And still argue that I can go for infinite length just by having EDFAs as repeaters. But that's not the case, simply because this large length 70 kilometer cannot really support the rise time budget. Let's see how to work out that. So just to clarify, this is the electrical spectrum corresponding to the low pass filter at the receiver. So we say that if you have a 10 Gbps system, your bandwidth is required is only 5 gigahertz, right? As far as the optical spectrum is concerned, this is the optical spectrum. The first null for NRZ appears at carrier frequency plus 10 and carrier frequency minus 10. So the total system rise time given for a 10 Gbps for the fiber rise time, given that, see, in this question we said that let's ignore the transmitter rise time and the receiver rise time. They are way bandwidth way higher than what is required for 10 Gbps. We are considering only the limitation posed by fiber. So tau fiber is 17 picosecond per kilometer nanometer. That is a dispersion of a standard single mode fiber, multiplied by 70 kilometer, multiplied by what bandwidth will you take, right? So here is where it could be a bit confusing, which is why I have these two spectral pictures. When we say electrical spectrum, that it is B divided by 2, that is the equivalent bandwidth of the low pass filter of the receiver. Okay, that's 5 gigahertz, that's sufficient. But when you transmit an NRZ signal at 10 Gbps, this is how the optical spectrum looks like. This picture I showed you earlier also, the optical spectrum will have, after modulation, when you are trying to propagate through the fiber, it will have the first null at Fc plus 10 gigahertz, Fc minus 10 gigahertz. This is what is propagating through the fiber. So the dispersion seen by the fiber is because of this spread. And this spread is 20 gigahertz. The span is 20 gigahertz because it is ranging from Fc minus 10. Your signal has content from Fc minus 10 to Fc plus 10. So for this dispersion, so for this tau fiber where we take as dispersion times, dispersion coefficient times length times delta lambda, this delta lambda should correspond to the delta lambda between, or the wavelength spacing between the two consecutive nulls in your NRZ spectrum. And the nulls are appearing at Fc plus 10 and Fc minus 10. So the delta lambda is the wavelength spacing corresponding to 20 gigahertz. You cannot take it as 5 gigahertz because 5 gigahertz is something else. That is the bandwidth required by the receiver. Here we are talking about what are the allowed wavelengths in the fiber, and these wavelengths are the ones which are experiencing dispersion, right? So this is 20 gigahertz and we calculated 5 gigahertz was 0.04 nanometer. So 20 gigahertz is 0.16 nanometer, okay? And this product is 190.4 picoseconds. Allowed rise time for 10 Gbps is 70 picoseconds. So which means that if I just put a 70 kilometer fiber, the rise time budgeting will go for a fiber, because you cannot really, this fiber cannot really support 10 Gbps, this length of fiber cannot support 10 Gbps system because of dispersion. You see 10 Gbps would mean that this is 100 picoseconds. The spread itself is 190 picoseconds, which means the pulse actually spreads to its two neighboring bits on either side. So you have a large inter-single interference. The allowed spread is only 70 picoseconds, so that it is within this 100. The spread is within this 100 picoseconds. Okay, so that's not allowed. So 70 kilometer span does not comply to the rise time budget for one span. So either we have to reduce the span length to what number? To a number which corresponds to 70 divided by this dispersion, which is 17 picosecond per kilometer nanometer, 70 picosecond multiplied by 0.16 nanometer. You have to reduce the length to this number, or you have to do dispersion compensation. Okay, so allowed span length is 25.7 kilometer. Actually, you should anyway do dispersion compensation if you are doing multi-span link, because if you're going to amplify and then further you're going to attenuate and amplify, if it's a multi-span link, your length of the fiber is definitely going to be larger than 25.7 kilometer, which means that this kind of link definitely requires some amount of dispersion compensation, right? Simple rise time budgeting will not be sufficient. So if you have a multi-span link, The thing that you need to remember is that you should always multispan links are associated with dispersion compensation. You cannot allow this kind of pulse spreading to happen because of dispersion. Now, how do you do the dispersion compensation? You have to kind of nullify this effect. So our next lecture is going to be based on how to do dispersion compensation. But for now, let's assume that we have somehow done the dispersion compensation. Okay, and let's proceed with this link design to go ahead and find out what is the total number of spans allowed. Okay, so total number of allowed span is limited because of noise figure of the EDFA. So you had transmitter. You cannot imagine that you can keep introducing EDFA infinitely, even receiver. So even after assuming dispersion compensation, because every EDFA compensates for the gain, but it also adds the noise. So the noise added, so if the noise figure is initially, if you do an SNR map, you had an SNR which remained constant throughout the link. The fiber does not change the SNR. The SNR at every EDFA will start degrading the signal. So this is OSNR map. The OSNR will start reducing after every span. So then what will happen is you will not have the sufficient SNR and so the sufficient Q value at the receiver to successfully demodulate your signal. So to do that, you need to recall what we learned in EDFA. So this is the output of the EDFA. This is the signal. You have the noise all around the signal. Okay, so this corresponds to the ASC filter of the EDFA. So the power spectral density of the amplified spontaneous emission, the power spectral density, the optical power spectral density is, we derived that it is 2 NSP h nu g minus 1 times the B, where B is the bandwidth. Power spectral density is just this multiplied by B will give you the total power. When you allow this to fall on the signal, you have the signal beating with the ASC. Now this ASC can be at all this band. So we calculated the electrical power spectral density of the ASC signal beat noise last time, and that turned out to be 2 RD square P sig rho ASC. You substitute for rho ASC from here. So this is the expression you get. We want to now relate the SNR and OSNR. SNR is the electrical quantity which decides your Q and Q decides your BER and so on. Whereas optical to signal to noise ratio is something related to the noise power added by the amplified spontaneous emission. Okay, now we want to relate these two so that we can calculate what is the effect of the EDFA. So the output SNR after the EDFA, right? So your signal is, so this is P in, let's say G is the gain of the EDFA, and let's say this is falling on the receiver. So G times P in is the power falling on the receiver. So RD times G times P in square is the signal power divided by the noise power. The noise power is contributed by the short noise and the signal ASC beat noise. We don't think about thermal noise here because once the signal is amplified by the EDFA, we assume that the power output is much larger and so it is operated in the short noise limited condition. So that's why we don't take thermal noise in an EDFA operated system. Okay. So 2QG RDP in delta F is a short noise and signal ASC beat noise is the noise introduced by the EDFA. Now let's make an assumption that the signal ASC beat noise is the one that is dominating. Then the SNR is just this signal ASC beat noise, which is this number which we saw in the previous slide. Now you can cancel out this two, one RD you can cancel here. G times P in is P sig, right? So sorry. So that's can get cancelled. So one of that is can get cancelled. So you get something like RD G P in divided by 4. If you do the simplification, you get some number which is corresponds. So you can cancel out this G times G and G minus 1. You can approximately, if it is large gain system, you can approximately say that this is RD P in divided by this number, which is 4 NSP, so this RD also gets cancelled, so it's just 4 times NSP H nu delta F. So this is the SNR. Now OSNR is signal power divided by noise power. Now the question is, when you do noise power, what is the bandwidth? So traditionally people started using 12.5 gigahertz, which is as the reference bandwidth. Okay. Now there's no specific reason why 12.5 gigahertz. It actually is related to the resolution bandwidth of the optical spectrum analyzers available at that time, right? So it turns out that the optical spectrum analyzers available at that time had a resolution bandwidth of 0.1 nanometer. That corresponds to 12.5 gigahertz. So the AAC power. So this is your so what is this reference bandwidth we are talking about? We are saying that when we put a marker on an optical spectrum analyzer and try to measure the AAC power, you will always put a marker here. So the marker will always measure the power within that resolution bandwidth. Okay. So if you were to do a signal power, so this is the output in the output optical spectrum. This is, if you put a marker here and measure, you will get P signal plus PAC. If you put two markers here and measure this power, so you have, let's say, PAC on the left side and PAC on the right side, you interpolate and you find out what is the PAC corresponding to the signal peak. That will give you PAC. So you subtract this number, you subtract PAC from this number, you get the actual signal power. And the noise power is this, what you put in the marker and measure. So AAC noise power, you can, so OSNR is nothing but signal power divided by AAC noise power. But you cannot measure it more accurately than the resolution bandwidth of the instrument. The resolution bandwidth of the traditional OSAs, optical spectrum analyzers, used to be 0.1 nanometer. So you always measure the amplified spontaneous emission within 0.1 nanometer or 12.5 gigahertz. That's why this reference bandwidth turned out to be 12.5 gigahertz. Okay, so it is signal power divided by noise power in 12.5 gigahertz reference bandwidth. So OSNR is, signal power is G times P in, noise power is power spectral density of AAC multiplied by reference bandwidth. Power spectral density of AAC is 2 NSP G minus 1 H nu, that is what we knew from here, 2 NSP G minus 1 H nu times reference bandwidth. Now you assume that we are operating in the EDFA in a large gain condition. Let's say the gain is 20 dB or the gain is 100. Then 100 divided by 99 is almost equal to 1. So you can cancel this. So you have Pn divided by 2 NSP H nu B reference. And these B reference is what we said is 12.5 gigahertz. So, but I know that Pn divided by 4 NSP H nu is actually the SNR. So I can write this as SNR out Pn divided by, to account for that 4, I multiply by 2 here. NSP H nu is contained in this SNR. There is delta F missing here, so I multiply it with delta F, and then there is a B ref. So this is a relation between OSNR and SNR. If I know the OSNR, so OSNR is something that you measure using a spectrum analyzer. You directly put the optical field into a spectrum analyzer. It will give you an optical spectrum. You can put markers and measure the optical signal to noise ratio. Measure that. If you put it on an electrical detector, the corresponding SNR is B reference divided by 2 delta F, where delta F is now the bandwidth of your detector. This is the reference bandwidth 12.5 gigahertz. This delta F is the bandwidth of detector. And this gives you the relation between SNR and OSNR. Okay. Now, how do you now calculate for N spans? Okay. So let's say you have transmitter, you have fiber, you have EDFA with a certain gain, a certain amplified spontaneous emission. You have a signal out. The second EDFA is giving you 2 times AAC. The third EDFA, by the time you have the nth EDFA, it will accumulate n times AAC, because each amplified spontaneous emission, it just keeps adding up. So for one span, the AAC is power spectral density of AAC is this. So PAAC, the power, AAC power is equal to 2 NSP hν into bandwidth. Now for a reference bandwidth of 12.5 gigahertz, this in dBm is actually, if I do want to do this in dBm scale, I'll take the log of 10 log of 2 NSP. Now 2 NSP is nothing but noise figure plus log of hν times 12.5 gigahertz, that corresponds to hν and this one, and plus log of g minus 1. That is what is simplified here. This log of 10 log of 2 NSP, this is the noise figure. This term, these are all constants. This is Planck's constants, this is frequency at 1550 nanometer, you can calculate 12.5 gigahertz. This number turns out to be minus 58, and log of g minus 1 is g in dB. 10 log g minus 1 is g in dB. So this is a very useful expression. So if I have PAAC out in dBm like this, the OSNR in dB will be, OSNR is nothing but P signal divided by P noise, signal output power divided by P noise. So OSNR in dB would be P signal in dBm minus PAAC in dBm. P signal in dBm is this, AAC in dBm is what we have calculated here, minus 58 plus NF minus G. So you have the relation for OSNR in dB in terms of noise figure and gain of the EDFA. Now after n spans, there is AAC addition of n times. So the noise power added is n times PAAC. So OSNR in dB is P signal out minus, now this has to be n times. So this will be 10 log n plus PAAC out, because this is logarithmic expansion of this, which corresponds to minus 10 log n. And of course, I have this PAAC out dBm as 58 minus NF minus G. So this is the relation, this is a very useful relation or approach that we will follow when we try to cascade EDFAs. So how do we solve for this problem? This particular problem, we calculated the receiver sensitivity, and we know that every span should compensate for a loss of 14 dB, and the noise figure is 8 dB. So the minimum SNR after n spans, I need to have, after so many spans, I need to have, at the receiver, I need to have 16.9 dB. Because this corresponds to Q square, SNR is equal to Q square. So Q square is 7 because BER is minus 12, 1E minus 12. So corresponding to that, the SNR required is 16.9 dB. I need this 16.9 dB as SNR after all the n spans. So minimum OSNR, so we go back, because for EDFA we know OSNR and not SNR. So from SNR we go back to OSNR. So you use the same relation, you find that corresponding OSNR is 15.9 dB. SNR times 2 delta F by Bref is your OSNR. So OSNR at the output should be 15.9 dB. But OSNR at the output is what? Signal power divided by signal noise, input noise plus n times the noise of the AAC. So assuming that the input noise of your input signal is very low, which is the case because you took 30 dB as your input noise. Of course, you have to remember that this approximation is not correct if the number of spans are very small. This n is what makes the n times PAAC much smaller, much larger than P in noise. So OSNR at the output is the relation that we wrote in the previous slide, which is this. So I can substitute here and find out what is the number of spans now, right? So I can find that the number of spans is, this is 58, minus 8 is the noise figure of each EDFA, 14 is the gain required in each span, this is the transmit power, and this transmit power is compensated by the EDFA, so that's the same as PS out, and minus 15.9 of course is the OSNR after each span. So it's just substitution in this equation. That will give me what is 10 log n. From that I calculate what is the number of spans that this system can support. Turns out to be the number of spans is 25, and span length we calculated is 25.7 if each span were to be operated independently without dispersion compensation. Of course, with dispersion compensation you can go all the way up to 70 kilometers, right? Assuming dispersion compensated, if you were to operate this span independently without dispersion compensation as a single span network, you should use 25.7 kilometer. Otherwise, you can, if it is dispersion compensated, you can actually go all the way up to 70 kilometers. That's what we saw earlier. So, turns out that the number of spans are limited by the EDFA because the EDFA keeps adding noise. But the length of each span is decided by dispersion. The overall length is also getting limited by the dispersion. And as I said, how do we increase the span length? You have to use dispersion compensation. So this is a very important idea for link design. So in the next lecture, we will talk more about dispersion compensation.